This is Viterbi Voices, your chance to hear stories about research, classes, student life, and more.
Directly from our students, faculty, and other members of our engineering community. All right here at the USC Viterbi School of Engineering.
Welcome back into Viterbi Voices. This is episode
122.
122. As usual, I am one of your co-hosts. My name is Paul Ledesma, Director of Undergraduate Admission here at the USC Viterbi School of Engineering.
And my name is Audrey Roberts. I'm a junior studying mechanical engineering here at USC.
Absolutely. In this episode, this is a little bit of a longer one. A
Yes.
little bit of a longer one. But I really think everyone needs to listen to this episode. We have Dr. Peter Beerel and Dr. Sandeep Gupta from our Ming Shea Department of Electrical and Computer Engineering here to have a broad and deep conversation about research that they do, what electrical engineering is, how that fits into the vast, complex issues that engineers deal with on a daily basis to make the world a better place. And I also raised the question that we've raised a few times before, which is, why are so many high school students interested in computer science but not electrical engineering? And we discuss it at length. It goes deep. I mean, this is like a Wired magazine deep dive.
Yes.
Right?
Yes.
I mean, and you stick all the way through toward the end, because at the end, I think Audrey and I continued the conversation about some specific stuff. So get in it.
Yeah, this is a good one.
Get in it and stay in it, and it's a good one, and I recommend it. Also, quick point, we mentioned this on a previous episode that we have new podcast equipment, and we're still learning the ropes. And so I think that we had a setting wrong where specifically me was like cutting out at certain points. I'm hoping you're going to be able to hear me okay, but you're hearing me fine now, so I think we fixed it.
We're working on it.
We fixed the setting, I think. But anyway, so sorry about that, but we promise to do better in the future. But stay tuned. Why don't we start with you at least introducing who you are? Peter, do you want to start?
My name is Peter Beerel. I'm faculty in the Electrical and Computer Engineering Department. Currently, I'm the Associate Chair of the Computer Engineering Division.
Cool, great.
I'm Sandeep Gupta. I'm also a faculty for almost 30 years in Electrical and Computer Engineering Department. I was the chair until last year of the department, and I teach in the area of hardware design.
Great, thank you. I think what would be helpful to our audience is to get a better sense of each of your backgrounds and a little bit more about where you come from and what you've done. And I know the faculty have a hard time thinking back to high school, and I don't want you to go back necessarily that far. But this idea of where'd you go to undergrad? What'd you study? How'd you find yourself here teaching at USC?
So I've tried to follow my brother. He was a chemical engineer. I thought that was going to be really cool. I went to Princeton. I went to my first chemical engineering class, and I completely hated it. Mass balances, and I remember getting a C on the first exam and saying, what is this? This is not what I signed up to be or wanted to do. I thought, what should I do afterwards? I considered computer science. I looked at electrical engineering, and I said, I just don't want to program for programming's sake. I actually want to have an understanding of the bigger system. I wanted to build things. And so I switched into electrical engineering, and then I've continued ever since.
And that was at Princeton?
That was at Princeton, and then I went to Stanford and came here and been involved in lots of different things, a couple of startups, and now doing more administrative stuff and lots of research in all sorts of different fields that I never thought I'd do, but it's wonderful. There's a lot of really tough problems out there these days that I'm able to work on, and it's been very rewarding.
So with in your last, maybe you're currently doing research or your most recent research area, what was it in, or what was the end use application of what you're shooting for?
So I think one of the things that Sandeep and I are currently working on is this is the concept of the end of Moore's Law. So right now the technology in your phones, the technology in the laptops are getting to the point where we can't make them as better every year. It's slowing down. Yeah. And we're all trying to figure out what the next wave of innovation is going to be driven on. And one possibility is this area of superconducting electronics. This is electronics similar to what's in the laptop, but will run at around 4 Kelvin. That's close to absolute zero. And so you can imagine a whole supercomputing building, maybe underground, where huge rooms are cooled down to 4 Kelvin, and our electronics will work on it. And instead of taking gigawatts of energy and requiring to be right next to a river to cool, this technology would be able to run super fast and super low power. It'll be much greener. It'll be and perhaps solve some of the big problems we have in terms of consuming too much energy and electricity to run our electronics and to run our Google searches and to run everything else we rely on. So Google might have one of these buildings that we hopefully will be involved with. There's other applications as well. I mean, people are now talking about quantum computers.
Yeah.
And those are really cool stuff where they're using quantum mechanics to run, and electrical engineers actually are building a lot of these things with physicists. But they don't know how to control them very well. So it may be up to us to develop the circuits to help control the quantum computers. And quantum computers will work at actually millikelvins, and then you could imagine our circuitry run at 4 Kelvin and their circuitry running millikelvin, and all relatively supercooled and working together to actually perhaps build the first effective quantum computer.
When you mean control, what do you mean by control? They're not like running out of the building.
Yeah, right. So there's these quantum dots or quantum circuits, but they actually need electromagnetic signals to come in to actually manipulate them, to actually run whatever program they're doing. So there's additional electrical control of these circuits that have to happen.
Got it.
So whatever is the basic phenomena, which is, it could be light, it could be any other type of, many types of signals are being used for that. They have to basically be, they have to be just so and controlled in the sense that they should behave in a certain, they should be put out in a certain way.
Yeah.
And they should interact in a certain way. And those interactions have to be just so for them to basically do useful computation. So it's that control.
Got it.
So we're going to translate.
That is necessary here.
We're going to translate a high-level program into all these control signals that manage these fundamental quantum little dots or quantum little circuits, right? And we have to do that in real life, right? It has to happen somewhere, right? So we'll build a chip that'll be right next to the quantum chip, and they'll work together to hopefully do this. So that's one of the areas we're currently looking at. It's pretty cool because it could mean, this is the next generation of technology that could drive things. It could be, driving things because of energy, or it could be driving things because we need quantum computers to do the next thing. But we are involved in trying to define what is that next big thing. For the last 30 years, it's been CMOS technology, and they've gotten better and better, and our phones have gotten better and better, and our laptops have been getting better and better. But, I haven't bought a laptop in 4 or 5 years because it's been good enough.
Mm-hmm. Right.
Right? What will drive that next better?
It's only been incremental.
It's going to get less and less. It's going to get even more incremental over the years because we can't push that CMOS fundamental technology that we've had for the last 30 years any better. We're getting down to those sort of physical limits.
Right.
And so something new has to happen. And it's
the physical limits of like transistors on a chip.
Exactly right. Exactly right. And something has to happen. I mean, or at least we'd like something to happen. We don't want to be changing and improving our technology as slow as battery technology or, how often do you change your laundry machine, right?
Yeah.
So we think we have the option to keep this sort of technology growth growing, but it's going to take another big breakthrough, and we're trying to figure out what that is in some of the research we're doing.
So, and Sandeep, I apologize. We'll get to your introduction in a minute, but then we just dove in here. This is fascinating. Given that everyone listening today understands that they have a mobile device in their pocket, they either have a desktop computer or more than likely a laptop.
Yeah.
When is that change? When do you foresee that change happening? And are you seeing quantum or superconducting computers going to mobile devices? Are we going to be having this in our pockets?
So we can't have it in our pockets
Right.
because we can't have a refrigerator in our pocket, right? So there's going to be a situation with 5G where these devices will probably not get that much better, but you'll be able to go to the cloud, and the cloud will be better.
So you relay the
the
computing
information
power.
through wireless technology, which other electrical engineers develop, right?
Right.
Through a wireless network that's high speed, that can deliver streaming and all that stuff, which more electrical engineers build.
Right.
But then when it gets into the point where you have a big building that Google or Amazon or whatever have that service all these requests, right, that stream Amazon videos and do all this stuff. That's where our technology may happen. And admittedly, it may be 10, 15 years down the road. This is where it gets really exciting. People would like it faster because we may see a slowdown of CMOS and there may be a gap where we can't do much. Right? We don't know. And this is where, everyone is looking to see what's going to be next and how fast we can get it. I mean, quantum computers have been an interest for many years, and it's relatively slowly gaining traction because it's a really hard problem. And so with the superconducting electronics, it's also sort of slowly gaining steam. But now, many people see it. The government sees it. There's research dollars to be had. And a bunch of us who normally did stuff in CMOS now see, okay, maybe we need to apply our skills, our technologies, our what we know to these sort of next generation areas.
Let's define CMOS for a second, because we've used that term a lot. And that's an acronym?
So it's an acronym. It's any complementary metal oxide?
So it's a particular way of making. There are many ways you can make transistor. Transistor usually has semiconducting material. So these are, they can be mostly silicon. The most popular one is silicon. And silicon by itself is sort of neither a conductor nor an insulator. It's sort of in between. But you can add a little bit of other materials to it to make it a little bit conducting in one way or another way. And so those are called N and P type of semiconductors. And when you put them together, historically we have put these together in a variety of ways to make transistors. But those transistors used to be very, very power hungry, and they used to consume a lot of power, and they used to be big because the currents would flow all over the place and they had to be separated from each other. So you couldn't put billions of them together in one small area. But CMOS is a particular way of using those transistors along with those materials, along with basically a layer of insulator that sort of is, imagine as if you basically have a plate and there's an insulator that there is a wooden there is a wooden plank, and one side you basically have a magnet, and when you bring that magnet, it sort of connects. It makes it so there are two buckets of two connections on two sides of this piece of wood, and when you put a magnet in between on the other side, it basically somehow connects these things together. And CMOS is a particular way where you use semiconductors along with this metal, this oxide, which is an insulator, and so that's why it's called. So the metal is used to be historically the place where you would apply a voltage instead of a magnet, and then an insulator that would separate it out, and then essentially these two areas of semiconductors that would then be either connected or not connected, depending on the voltage you apply on the metal part. It's not metal anymore. It's not been metal for a long time, but the name MOS stuck. And CMOS is basically because we use both the types of materials. As I said, you can take a semiconductor and add certain types of impurities and make them what we call N-type semiconductor, or other types of materials, impurities, and make them P-type materials. So it uses both N and P. So it's this particular way of making transistors.
Great.
That is CMOS.
Just maybe a little bit more on Moore's Law, because I was just teaching some middle school / high school students.
Oh, really?
The other week we had a camp at USC where we brought in middle school students from, well, my daughter was in one of them, and then we also brought in students from the local area and some faculty kids.
Yeah.
And so I actually gave a lecture on some of this stuff. So we were trying to explain. I showed them what a transistor looks like. I'm saying over the years we've been able to put more and more of these transistors on a chip. And I actually took a physical chip, took a hammer, broke the chip, and showed them this little tiny millimeter by millimeter, but shiny, so it looked like metal, right thing, and said, there's 1 billion transistors on this thing. Wow. That's how small we can make these transistors. And for people to recognize that, for your phones to work, for the laptops to work, that's what's happening. We have over 10 billion transistors on these modern chips. They're all CMOS. But it's getting to the point where, well, we're not sure we can get to that 10 billion. It's getting so small. And even when we get to 10 billion, it may not be that much lower power, or another aspect that becomes important. So it's been a huge evolution that's driven a lot of our technologies to be able to make these chips smaller and smaller and finer and more transistors. But if we stop being able to do that, stop being able to make those improvements, That's what's going to happen to our society that's been living off of this technological, revolution, I would say, over the last maybe 40 years, 50 years, right? So
this is why it's one of the grand challenges, which is systems beyond Moore's law.
yeah, absolutely. And this is what, we do and we're working on, and it's a fun and exciting time. But it's also, people like us, the world is expecting somehow this to keep going.
Now, you talked about superconducting computers. You talked about quantum computers, but these are different things.
Yes.
And then I'm going to add a different term that's in the zeitgeist, which is supercomputing.
Yes. So
are these three distinct?
So supercomputing just means, you have these massive rooms with massive amounts of these chips trying to do big problems. IBM has Blue Jeans. I think there was a lot of news where they can, run grandmaster chess, right? With some either machine learning or other types of algorithms.
Not Blue Jeans.
Watson.
Oh, Watson.
Blue Jeans is our video conference.
Sorry. No, there was another one, wasn't there? No, anyways, Watson. So correct. Yeah. So Watson, right?
And we have D-Wave. We have ours.
And that's our quantum.
That's our quantum computer.
That's our quantum computer. So supercomputing just
Well,
means...
some people think it's a quantum computer. There is a controversy about whether that is a quantum computer or not. And one of the
D-Wave.
The D-Wave is being used for doing experiments that will show that it actually has quantum effects.
Oh,
So there is a little bit of controversy.
interesting.
Company that builds it, of course, believes that it has quantum effect, and the community in general believes that it doesn't. And our researchers are essentially trying to poke it in various ways and do experiments on it to show some evidence that it actually is this thing. And so
So maybe it would be useful
depending on who you talk to in the field, they would basically tell you one way or the other.
I found this fascinating. What is a quantum computer and why is it so interesting? So from my perspective, there are problems that are really hard for us to solve, even with the current computers. They take, I guess one way to describe it is as the problem size gets bigger, it takes an exponential number of steps. Yeah. Really, really hard. Yeah. The power of the quantum computers is that somehow with the magic of quantum mechanics, they're able to simultaneously run an exponential number of these steps. So things that normally would take an exponential number of steps, long time, now may be fractions of a second. Okay? So the beauty of this would be many of our hard problems would then get easier, right? Actually, it also causes some dangers because we actually rely on some hard problems like trying to break an encryption algorithm. We like our privacy, right? And if it now becomes easier to break our encryption algorithms, what are you going to do? So even then, there are electrical engineers who now figure out, let's say quantum computers actually achieve their goal and can now do all these exponentially hard problems really easy. Yeah. Well, maybe we need a better encryption algorithm, which is even now quantum resistant. Huh. So even before quantum computers have proven that they can do what they say they can do or what they might be able to do, people are starting to research what if. And how are we going to protect our data and have privacy and have all these other things simultaneously? So that's kind of an interesting thing because research and these kinds of things take years to develop. So we can't just wait without doing the what if.
Yeah.
Right?
That's fascinating. So we're reaching our limits of CMOS, which means that the limits of new technology and iPhones that were just announced today, we happen to be on the announcement day of iPhones today. And so people go nuts.
All right.
And computers are incrementally and even slower.
Yeah, incrementally improving. Right.
Incrementally improving. But the research that you're doing and where you see the next step going are these superconducting machines or quantum machines that are cooled to a certain set of 4 Kelvin. And then 5G is not just about being able to have faster connections, but the ability to have those relay connections to use that computing power, which means that our pocket devices are actually more powerful as a result of that connection. Right, so 5G is not a faster phone network. It actually means a whole new world.
It does. And, it also will enable more mobile devices to mobile devices. I think that's one of the things where they have autonomous vehicles. Right. Another area where, some of our colleagues are involved with, where now we can have cars talking to cars. Right. So 5G has other impacts more than just our phone being able to talk to a good supercomputer. It's going to enable our car to talk to the neighboring car, and hopefully they don't lie and they avoid a crash.
Essentially, every cool thing that everyone's ever heard of is reliant upon work being done in electrical and computer engineering departments right now.
Oh, absolutely.
Well, so I actually talked to a couple of our undergraduates last year, and I basically said, why don't we think about electrical engineering in the broader sense? This is the argument Peter and I were having the other day when you basically asked us to come here.
Absolutely.
And so we basically decided to, so I asked undergraduates, I said, these were second-year undergraduates, Cami and Chloe. And I was telling them, I said, I'm an old guy. Can I look through your eyes to see what the students would find interesting about this thing? And so they made a long list. And I sorted the list into 3 buckets. And those buckets actually fit very well with life, liberty, and pursuit of happiness. So life is basically, things that we've done in the past, and in some sense we say we conquered them. Refrigeration, air conditioning, heating. Electrical engineering has played a big role in those kind of things. Pumping water, you have piped water. So you cannot imagine life without this. But there are many topics within that bucket that are still very active area of research which actually have the potential to change the world. One of those areas is basically energy. So think about energy. When I grew up in a small dusty town in the shadow of a steel factory, which actually made me think about becoming an engineer, but we don't have to go there.
You can go wherever you want. That's the beauty of this conversation.
So basically, when I grew up, I couldn't leave a room without turning off the light or being yelled at. That has become a non-issue now. Essentially, we have eliminated the energy requirement by a huge factor for the lighting energy required for illumination. It's deemed to be, but yet, according to some estimation in US alone, we'll save something close to $500 billion over the next 20 years in basically because of this innovation, which actually is electrical engineering innovation. It's LEDs instead of, all of the light bulbs have been electrical engineering devices, but LEDs are some things that are fabricated like semiconductors, the CMOS chips that you're talking about, all of these things. They are in many ways basically product of the same manufacturing process, some of the same materials sometimes.
Yeah.
And these are basically growing by leaps and bounds. Now, the efficiency of LEDs we have achieved close to, as a colleague of ours, Dan Dapkus once told me that I like to basically propose projects where I can at least achieve a factor of 10 improvement. And when it comes to LEDs, there is probably not a factor of 10 improvement, definitely not, provably not a factor of 10 improvement in how much more efficient you can make them. But there's more than a factor of 10 improvement in the next 20 years in the cost.
Yeah.
Which right now, if you go to the store, you will see the difference in the price of the LEDs. Right. So still there's an opportunity, basically a huge opportunity for the next 20 years for researchers in electrical engineering to make a difference. Same thing in solar cells. Dan actually had a project working with several of our colleagues here who basically worked on a project. And again, his hypothesis was that, again, there is not a factor of 10 improvement in efficiency of solar cells, but we can make them 10x cheaper. And they did come up with a way to basically make them 10x cheaper by, instead of having the semiconductor material, which is quite expensive to fabricate throughout the entire surface, they came up with this idea of basically having just little islands of this material. And they basically placed the islands in optimum ways and designed the size and the spacing of those islands in such a way that it basically, for a tenth of the cost, it would essentially capture the same amount of energy, more or less, per square inch. And so there's energy sector is basically being revolutionized by developments in semiconductors, which is really cousins of the CMOS and other things you're talking about. Yeah. So this is sort of an area that is extremely active and, of research, and it actually changes the world in fundamental ways. It is very cutting edge technology. It has hard physics problems. It has hard math problems. It has hard electrical engineering problems. And actually, if you ask me, that's what electrical engineering is. Electrical engineering, you can be actually a physicist, primarily study physics and be an electrical engineer. You can primarily study certain types of mathematics and be an electrical engineer. Or you can be like me, who studies electrical engineering and be an electrical engineer. But this is the span of this field. Yeah. The only thing that we have in common is that we basically somehow, in the old days, what used to be common to all of these people who called themselves electrical engineers is somehow electricity was involved.
Right.
But so many methods and other things that we have developed that actually have absolutely nothing to do with, they're being used for things which have nothing to do with electricity. So another example I would put up basically, which is a segue for me to kind of talk about the next topic, is this semiconductor fabrication technology. These transistors, building billions of transistors in square millimeters of in square centimeters of space, required basically this massive innovation in basically, handling materials, managing lights and lenses, and these are like photographic printing process on steroids, so to speak, or inverse steroids, because they don't bulk you up, they shrink you down. So I don't know how to define that, one by steroids maybe. So you basically have this process, and one of the great advances that process enabled, those fabrication processes enabled, is genome sequencing. You can't think of something far away. When genome sequencing project started, it used to be done in test tubes that you and I have held in our high school classes, right? They used to basically mix chemicals in those test tubes. Now they are being held in these microstrip lines, which are essentially micron wide. These are tiny things that are etched on this thing, and the liquids, basically the amounts of material you require is fraction of that. But all of that thing is one of the, of course, there's a lot of innovation coming from the genome sequencing people. And people who do computational biology, and people who understand genetics, and who study the wet science, the chemistry and other things that go, biochemistry that goes into that. But the essential fabrication process that actually has enabled them to miniaturize everything and make it much more cost effective, so we can basically send out our materials to be we can sequence the genome of this and sequence all the genomes of this animal or that animal, is because of this fabrication process. So now what has happened is electrical engineering has actually contributed some of its basic methods and its wins that it has developed over the 50 years in case of semiconductor fabrication for the CMOS chips and all the chips that are in your iPhones and your laptops, into basically industries that basically have nothing to do with electrons in some sense. Nothing to do with moving and controlling electrons and making them do our bidding. So biotech is basically another area. Biotechnology, ultimately if you go to basically, for an MRI magnet is an electrical engineering device. And, you can develop a lot of machine learning and fast algorithms to basically take the image that you get from it and clean it up to make something useful for the doctors to see, for the physician to see. But people who know a lot of computer science can basically do that. But what is necessary is that if you know also the electrical engineering of that magnet and how it interacts with the human tissue, if you understand that, then you can say, I'm not dealing with some, to me, the signals are not just some signals coming out of unknown black box. These are signals coming out of a magnet that I understand. These are signals that are coming out of this. These signals are interacting with human tissue, with liquids and other things in the human tissue that I understand. And if I understand that, then I'm not trying to clean up an image that has some arbitrary noise. I'm trying to fix an image which has a noise that I actually know mathematically what it is. And so using that principle, our colleague Justin Haldar who actually spoke in that video that you listened to, who talked about accelerating magnetic resonance imaging, this thing. He's been able to show that he can do MRI 6 times faster. I mean, I've been lucky enough to go to the MRI only once, and I thought I would basically show up at 6 o'clock in the morning and I'd be out by 5, 6, 10. And then the guy puts me in. I'm already feeling claustrophobic. I didn't know I was claustrophobic until they put me in. And the last words I heard is, our study will be for 40 minutes. Wow. Okay, now that 40 minutes becomes 6 minutes, using techniques that Justin is this thing. So you can get the same quality of image in 6 minutes instead of 40 minutes. And so that's
huge difference.
6-7 minutes instead of 40 minutes. And that's a huge difference. But that comes by basically not only the mathematics and the computer science of cleaning up images, but you combine it with your understanding of the electrical engineering, then that's unique enhancement is possible. And that enhancement can be done essentially by people who sort of are in electrical engineering.
So maybe so what are we doing? We're blending computer science programming, deep understanding of the mathematics and physics. Right? And when you blend those together and you like all those three and you want to figure out how to, impact the world, that is electrical engineering.
Yep. Why does nobody get it?
It's hard. It's hard to think that.
When I talk to the students, a lot of times, when you're a professor, your friends and neighbors and people you don't know bring their children to you to get some career advice.
Right.
And I talk to the students and I say, what do you like to do? Yeah, something in engineering. That's why my mom brought me to talk to you.
Right.
But, I also want to do some social good. I said, you know what? You can do, first of all, speak here first as an engineer. I say you can study any part of engineering and not worry about doing good for society. I mean, every area of engineering basically will allow you to do that. Yeah. But whatever good, more importantly, what is important is whatever area of good you think you want to do, you can do it in electrical engineering. I say now I speak as a partisan.
Yeah. The bias source.
The bias source, right? So I disclose my bias and I say you can do it as an electrical engineer. So I say, no, I want to study environmental engineering. I said, yeah, one of the ways you basically improve the environment is basically capture all these particles before they leave the factory chimney. Yeah. You use electrical precipitators to basically do this. And basically, if you can grab them in an energy efficient manner, you can grab the particles, as many particles as possible. There are electrical engineering processes for that. Of course, there are other methods that use chemicals to scrub the effluents before they go out in the air.
Right.
You want to basically do salination. And, I used to be very worried about California running out of water. I'm an old guy and I begin to worry about things like this. And then I realized that the cost of desalination is basically now only 3x of the water that we get from the rivers.
Really?
Oh.
Yes. So basically it's only the plant that came up in Carlsbad essentially operating at about 3x the price of water we pay to come from Colorado River.
That's a big difference.
That's it's still a markup, but
But
really,
we have a lot of salt
we may
water.
not be able to. But we may not be able to, in our agriculture sector, we may not be able to grow alfalfa, but we can still grow strawberries and wheat and corn. And in our homes, we will still be able to drink and have showers and so on, but we may not be able to have the lawns.
Yeah,
and so I sleep better, right?
Yeah.
Now,
and we're about to have a lot more salt water pretty soon.
But what about desalination plants? What about desalination plants? Our colleagues, our own here at USC, we have a water lab where our colleagues in environmental engineering are developing membranes and other technologies, which are, at biochemical level, they basically understand the materials and so on and so forth. But ultimately, the main cost of this is electricity.
Yep.
The main cost of basically this is electricity.
This is Kelly Sanders' research project, the water energy nexus.
And nexus, right? So it's inextricably tied to the energy usage and basically the footprint that we put on energy, which has all kinds of implications. Better solar cells, more economical solar cells. You basically reduce the carbon footprint of yourself, right? You basically reduce the effluents you put out in the air. You put the monoxide and dioxide you put out in the air. So essentially, you cannot touch any area of engineering and not touch people's lives, hopefully for the better. Right. And you cannot touch any part of electrical engineering without actually influencing people's lives.
Absolutely.
So I sort of,
that was life.
That's life.
I was going to say, we didn't get to
liberty. We didn't get to liberty, right?
Pursuit of happiness is self-evident. To quote another,
make things better, fun.
To quote another thing from the same document or the same body of documents by the original founding fathers. Okay, and the pursuit of happiness is straightforward, right? I mean, if you basically want to, without compression, you wouldn't have MP3.
Right.
Okay, and it's this thing. You couldn't without compression. You couldn't have video streaming. Without computer networks, you couldn't have video streaming. Right. So you cannot imagine a world where essentially these things don't exist. Right. The games, just when I was a child, the games used to be blocky and this thing, and now the games look realistic. Not only you have them, you basically have them with virtual reality, as you mentioned. So you essentially, pursuit of happiness is sort of, very sort of obvious, I think. Every 16-year-old, every 17-year-old should understand that the revolution in the pursuit of happiness, is something that
they enjoy doing.
That the electrical engineering has essentially deeply enabled. The circuits on which these things run, the ideas in basically how to communicate and how to compress, how to manage the whole thing. Even some simple ideas like, where to place the content. I mean, companies like Netflix would basically, if they put all the content in one server and everybody wants to watch that, there would be a problem. But they essentially, even mathematical ideas which essentially determine what are called content distribution networks. So essentially, instead of keeping all the content in one place, you sort of figure out where people are using it,
Right.
and then put copies basically in all of those areas. This
Yeah,
is
these
an
are
idea that
referred
is
to
called
as CDNs.
this, and so the CDNs basically do this, and this idea of caching actually comes from computers, and other things have basically essentially done caching of your data.
And this goes back to the computer you were talking about, Peter, with this idea of like these super or these quantum
Yeah,
computing.
we're going to have
powers.
we're going to have to maybe have more of these supercomputers in different spots of the world, right?
In the different parts of the world, and
Because
you
then
basically
to download this one particular video, I'm not connecting to the East Coast. I'm connecting down the street.
Right.
and
Which are
sometimes
like Amazon distribution centers, to be honest.
And
Yes,
sometimes
exactly.
you're not connecting it to one in LA because it's already loaded. So you are actually connecting to the one in East Coast because that's faster.
Interesting. But
So-
it's going to make a smart decision.
But it's going to
based
make a
on-
smart decision based on that. And all that smart decision would be called, by depending on who you talk to, would be called a sort of an optimization of content distribution network, or would be called a control person. All of these are specialities in electrical engineering.
I think that's the hard part is that people don't think of electrical elements as being physical. They like wireless communication.
Yeah.
It's magic. It arrives.
They don't realize that someone had to develop it, and there was a lot of electrical engineering, if not all electrical engineering, doing that development, right?
But they do recognize and understand Amazon distribution centers. They understand that there's a physical piece and that's to get from point A to point B. But that's the same exact thing to watch that video on Netflix.
Yeah, yeah.
So the underlying physics of basically the information infrastructure, which I would include, as I said, I would include solar cells and LED lighting in that.
Yeah.
I would include MRI machines and other things in that. I would include everything that touches your computer games and your video and audio and distribution and all that stuff.
Right.
Anything that maintains the data part of banking, security, everything. Everything that is physical is going through electrical engineering device.
And I think people think that because things become digital, they're no longer physical. And that's the point that we need to.
They lose it. Yeah.
Yeah, we need to dispel that. We need to talk about the physical.
And because they're wireless, they think it's not, as you said, right? But just because it's not wireless doesn't mean it's not physical.
Yeah, I think also as a mechanical engineer, I can't imagine a scenario when making a piece of hardware where it wouldn't be working with an electrical engineer. And I think that's what's so exciting and kind of something you've demonstrated as well in this conversation is like, everything ultimately links back to it. For example, on a computer, the, mechanical enclosure is constrained perhaps by the size of the PCB, or 5G, calls for a different kind of enclosure. So I think that's a really exciting thing too, is that, and quite honestly, I don't think I've ever made anything, and it's also because I gravitate towards hardware and towards those projects. I don't think I've ever worked on a project where I wasn't working with an electrical engineer.
Right, especially because this last summer you were at Microsoft and working on devices.
But even at USC, like in Rocket Propulsion Lab, I'm on the avionics team.
Ah.
So the sort of link between that is so evident to me, and I kind of don't think about the software. But it's so cool to have sort of this physical constraint on something that's almost unthinkable, like we were talking about earlier, how small these chips are. It's incredible.
I want to put a pin in our conversation, but I like where this is going because, Sandeep, you didn't get a chance to introduce yourself. And I know we're like however long into this conversation.
So as I said, I grew up in a dusty town, which only thing that it had going for it was the rice fields. When they discovered, when India became independent, they discovered that it was one of the few places in India that had iron ore mines and limestone mines and a source of water all within 100 kilometers of each other.
And where was this?
And this is in the middle of the country, a place called Bhilai, which was one of the largest steel plant for first 40 years of India's existence. And whenever you basically find this big iron ore deposits and big limestone deposits and water in the same place, you somehow find a way to make energy there, and then you basically build a steel plant. This is basically how steel plants are sited. And so I grew up in the shadow of the steel plant, and I went to, my family had been there for hundreds of years before this. My great-grandfather traced family back to about 300 years before me. But many of my family members basically either lost or made out like a bandit in selling their completely unuseful pieces of land under eminent domain to build the steel plant. Some of them made some money, some of them lost a lot of land, but nobody was crying because this was terrible land for agriculture purposes. And the steel plant came up, and I went to school with kids basically, and almost every kid in my class, basically their fathers were engineers at the steel plant. So I grew up in the shadow of engineering in that sense. And that was sort of my journey to electrical engineering. When I went to college, to counter your point, some of the courses I really, really loved were mechanical engineering courses. I had to study, strengths of materials. I had to study structures. I had to study thermodynamics. I loved those courses. Even today, if people ask me some of the most surprising things about engineering that I have learned in my life, I ask people very simple question. I say, this rod here that is holding up this microphone, is it hollow or is it full, solid?
I don't know, actually.
And it's hollow. And the reason it is hollow is not because they're just trying to save on the cost, but they're actually trying to save on the cost and make it stronger. And that's so I learned, I love every aspect of engineering. I speak here as a lover of all things engineering. And I ask people, I said, I asked yesterday, day before yesterday it came up, and I was asking a 7-year-old. And I said, which one would be harder?
Right.
And the 7-year-old thought for 2 minutes. And he said, the pipe would be harder, to bend.
Right.
And I said, why? He said, because you'll have to bend also the insides. And that's exactly what the basic property of this thing is. That makes this thing. So to me, engineering is, I somehow was an engineer before I even went to college.
Yeah.
Electrical engineering grabbed me more than other things in ways that I basically, cannot explain. I would have been happy being a mechanical engineer, but that's not, I went to a school where you sort of was hard to get in, but once you got in, it was hard to move.
Right.
And frankly, I had no desire to move. I was very happy with those courses that I took in mechanical engineering and other areas, but I was happy with electrical engineering. So I continued on. And I moved from the area of controls, which Peter was talking about earlier, about controlling things, where you would learn to basically control mechanical things. You'll learn to control electrical things. Temperature controller is, for example, a simple example of that we use all the time. But there are complex things, like things that control your, you're flying by wire in your cars. Your airplanes have a lot of these control systems. So a lot of things, there are airplanes that would never fly unless there was an electronic control system in it.
Right.
So I sort of used to be in that area, and slowly I gravitated towards computer. And I'm in basically the area of hardware, developing software to design hardware, because when you have billions of transistors, you cannot design by hand. Imagine basically trying to design an entire city, right. An architect trying to design the entire city by drawing by hand with
physical pathways.
Physical pathways, right?
Yeah.
So you basically have to rely on essentially this, and not only that, you're not even using computers to draw. You're using computer algorithms to do the design itself, right. And that's what Peter and I primarily do. And the question basically that we have basically been, in some sense, people like me have actually not fueled the Moore's law, but we have been the beneficiaries of it, right. Because the Moore's law essentially has been doubling the number of transistors you can put in a cost-effective chip. So it's actually, people think it's a law of engineering. It's neither a law nor engineering. It's actually a set of economic forces. What is physically possible, what is economically viable, is all mixed in there.
Right.
What is organizationally possible, because economics basically means that can you manage this process?
Right.
And it has all sort of mixed in, and essentially has given this, and it's not a law because it was an observation. I would recommend that you look at that paper. Literally, Gordon Moore had 3 data points. He plotted them by hand. And then he extrapolated and he drew the line like this. He took 3 points and then he drew a line like this.
On a log graph, yes.
On a log graph. And it was a logarithmic graph, so that becomes exponential. So he literally took 3 points, and these are, all the 3 points are like in the little, 1 centimeter for the graph, and the graph is 10 centimeter by 10 centimeter. So he drew this long line from 3 points.
But it is interesting. It's like, so we're electrical and computer engineers, and our job is to really build software. Right, and there are about 3 companies that master this
for the purposes of hardware.
For the
design
purposes
hardware.
of hardware, so there are 3 companies that master. All of our graduate students go there. They have some very, very high percentage of electrical and computer engineering PhDs working with them, building this software. It's 1 million lines of code or more, and then they sell it to people who want to build hardware. because that's the only way to build these chips that have so many transistors effectively.
So study electrical engineering to write software so that the hardware could be built.
You understand
That's not the whole reason, but that's
that's one reason. And people don't realize that electrical engineers have to be experts at software, but it's not just software itself. We actually have to understand the hardware because we're trying to write software that builds good hardware. So we have to blend the knowledge of the hardware, the knowledge of the computer science algorithms, find out which ones match, and build software that can last for 10, 20 years and build on top of each other, good software engineering skills. And this is all, this is
So
what
let
we
me give you a
do.
very simple example, right? You have to be, just like you have to be an architect to decide what is the right way to provide these 3 labs that we need, right?
From an aesthetic point of
From from an aesthetic point of view. A structural engineer to decide basically how to basically support them all and build the roof and walls and so on, right? Now, that's the same way you have to be an electrical engineer to understand, how exactly to orient the transistor, how big should it be, how they should be connected to each other to basically do the addition or multiplication that you're trying to do. And do it fast and do it in less energy. Now that knowledge basically means that you essentially have developed over the years, you have developed either systematic methods or some hunches or design guidelines to basically say, hey, if you do it this way, then it is provably the best adder you can build. If you do it this way, then it is probably the most efficient adder that we know how to build, even though we cannot prove it. But at least experience for 50 years says that this is what we do. So our students have to understand that. So there they are electrical engineers because they understand something about electrical engineering design using these advanced transistors. But then they also have to put on a different hat. You say, I know how to do it as a human being. How do I make a computer do this? Because the computer doesn't get tired. The computer doesn't make mistakes as long as I write the code properly.
Right.
So how do I now take that problem? So I know transistors. I know many rules for connecting them to each other. Some of these rules are provably the best way to do them. Some of these are not provably the best way to do them, but this is the best we know. And it seems to work based on our 20 years of experience with this. Can I take all of these methods that we have developed for manual design by humans to do this thing? But now these things are becoming too big for us. So can we actually build this complex software? And those software are some of the most complex ones. So our field basically employs the percentage of PhDs to non-PhDs in our field is extremely high.
Yeah.
It's some of the most expensive software written per line of code because you basically need people who basically have this sort of two minds. They understand hardware, they understand software, and you don't get that kind of a training in these 2 domains until you've spent many years under the banyan tree. Which there were many in the dusty town I grew up in.
So I think that, first of all, thank you. These are all helpful points, and I think it's helping our audience understand a little bit more about how electrical engineering works. But the reason that I asked you in here, and this is exactly why I knew that once we started talking, it would just keep flowing, and it's perfect, so it's great. But to bring our audience up to speed, is that we were having a conversation last week. It was last week.
Last week.
About disparity of interest in engineering disciplines, and specifically from a high school perspective. And this isn't a USC specific problem, but that students are coming out of high school and for some reason are just nuts about computer science, and for lack of a better term, aren't nuts about a number of other disciplines, and they're not nuts about electrical engineering. And we were debating the whys, or how to explain it best, or how to talk to that audience a little bit more, because we have a theory that a number of those computer science interests are actually electrical engineers once they start to learn a little bit more about them.
So let me. I spent some time, convening when I was a department chair. We had 6 or 7 meetings with mostly our associate professors in the department, and the idea was that you guys are going to be here for a long time. So you should shape the next generation of thinking about what our field of electrical engineering should be like at USC, how we define it.
Right.
So the idea was to basically look at that. And if I were to distill my takeaway from those conversations that we had with a lot of, and I had a lot of side conversations with a lot of other colleagues who were not able to attend those meetings. And the simple way I try to distill it down so that I can share with myself really and my colleagues is the following way. Electrical engineering and computer science share the fact that they are about information. So this is about information. At the end of the day, what we do is we are in the information business. We are processing information, we are gathering information, we are communicating information, information is our coin of the realm. Transistors are just way of basically, doing all of those things about information. So they're for storing information. We do all of those things. So then what is the distinction? So if you're interested in information, you EE or CS, ECE or CS is your thing. Okay. Now, within that information, what has happened is that some time ago, we actually took two different paths. Computer scientists basically took at the path. They saying that the information, yes, it's about information, but your transistors are too complicated. It's very difficult for me to master the transistors. And you know what? I don't really have to master the transistor. I just have to basically sort of write my code sort of in material of what the transistors are underneath. I don't have to even worry about the computer architecture you're using. So they would build these machines, this software, which is say, it doesn't matter whether it's a Mac or a PC or whatever. I can run the same code because I build these layers and layers of software. And below that is basically your chip. So sort of, you guys can do your thing, we can do our thing. Yeah. So essentially what has happened is that over the last 40 years, computer scientists have essentially liberated themselves from the physics of the information processing. And so they have become more abstract. Right. So the way I think about is information is EECS, but information plus abstraction, built on abstraction, information systems that are built on abstraction is computer science. And it's a great thing to do.
Right.
Electrical engineers by and large have said, no, we are also in the information business, but we are by our origin and by our preference connected to the physics, the physical world. Right. To us, the wireless signal is physical and real.
Which is what we were just talking about a minute
so
ago.
that goes to show, so we will use a wider range of mathematics. I think it's, we dig a little deeper. There was someone who was looking at machine learning graduates recently and saying, okay, machine learning sort of taught in computer science and electrical engineering. But the electrical engineers will be taught more of the mathematics that make machine learning work, whereas the computer science will learn it from a point of computer tools, software kits that they can bring down from the web, plug and play, and get the system working. We sort of believe and harness the underlying mathematics. So if a high school student likes math and some form of physics, though some of us abstract above the physics.
We
some of us.
But you have to think about physics in a different way. I don't think we'd abstract about physics. So, for example, my colleagues in communication, when you're sending a wireless signal, you designed a signal and you sent it over the air. The air will basically put, when it reaches the other end, it would not look like what you sent because there would be all kinds of electrical interference from power lines, from spark plugs of cars, and so on and so forth. So when the signal reaches there, it's kind of dirty. Mm-hmm. So that entire thing is basically the way it becomes dirty. If you can mathematically model that, this goes back to the MRI example I gave you. Mm-hmm. If you know how the magnet and the body modify the signal so that which you like, because that's what you're trying to capture in imaging, but it also distorts, which you don't like. But if you understand how it distorts, you can basically come up with a more efficient way to get rid of it.
You can reverse manipulate.
You can reverse manipulate. That's exactly what error correction and all communication is about. Now, we may think about this as they would call it physical layer. It's not physics as in, it's not quantum mechanics, but it is physics in the sense that it is capturing a physical reality in a mathematical model. Yeah. So when I say physics, physical,
general,
I mean in that sense that it's a communication channel, air between here and here and my self tower, which may be 700 kilometers away from here, is a physical medium. We have mathematical models that tell me what is the most likely ways in which it will distort the signal I sent. Mm-hmm. And by knowing that, I can come up with a super efficient way to correct that error and get the signal and make my conversation tangible. So I'm not using the word physics in a classical sense. I'm using the word where the physical world is actually impeding on you.
And it's important to recognize that if you take physics in high school, you may not see that perspective, right? Because the physics in high school will teach you probably just a small fraction of mechanics, right? In AB physics or whatnot. So they're not, describing the full realm of physics at that point, right? But if you do like, physics is a lot of math and it's applied math. If you like applied math and programming and like to solve real problems and problem solve, I think that's where we should be, where I think you'd be happy as an electrical engineer.
Yeah.
Right?
So you're building a sensor, which is a device.
Right.
And a sensor, let's say a mechanical sensor that senses how much force you're applying on this. So you're building a sensor that goes in the building on a beam to decide how much is the beam bending too much or is being put too much force being put on it.
Right.
That sensor is ultimately a mechanical engineering device. Okay. But understanding and modeling of that sensor, because that sensor is a device that actually has certain properties that you can measure. Okay. But it has properties that are good properties, which makes you use it as a sensor.
Yeah.
But it also has some non-ideal behavior, like a gas gauge in your car, which may not be completely uniform, right? A gas gauge in my car goes, stays at full for 100 miles.
Yeah,
and then it starts to drop sort of reasonably well. And after a quarter, it just collapses. Right. Okay, that would be basically, so there's a physical device that's a gas gauge that somehow senses the amount of volume, which I like, but it also has imperfections that causes it to behave in this way.
Or more modern sense, the range. Range to empty. Range to empty can change based on behaviors.
I have a natural gas car, and the gas stations are 6, 7, 10 miles apart, and I have the greatest range anxiety because unlike electric vehicle, you can charge somewhere.
Yeah.
I don't have anything in the next 10 miles. Okay, so I have range anxiety on this thing, and it goes all over the place, right? So most of the physical world devices have properties that we rely on, that we want to harness to build a system, build an integral part of our system. But they also have a lot of this sort of noise or they are not ideal.
Right.
And understanding that non-ideality, capturing them in a mathematical way, and making sure that you take care of in how you design the information system. It's an integral part of your information system design, which actually works around these non-idealities. So you're solving some of the hardest problems to build the abstraction that then other people may be able to basically worry. The computer scientists don't have to worry about this abstraction because we do.
Got it.
But the abstraction thing is here. Here is where I come to this. I have given this challenge to my students for 3 years in a row. And I tell them, I said, take something like Moore's law, something that has basically become twice as many transistors in the same amount of area and at reduced cost every 18 to 24 months or 30 months. For 50 years. I say, go find one other thing in the universe that has actually grown at that rate for 50 years, 40 plus, 45 years already, since Moore's paper in 1964. And they can't find anything. I've asked them to look at aerospace things, mechanical things, domes, civil engineering things, domes, bridges, tunnels. Right. I say, find one technical parameter. Catalysis, chemistry, biochemistry, viruses, antiviruses, immune vaccines. I give them 40 different examples. I spend half an hour writing all the possible areas they can look at.
Right.
And the students have not been able to find anything that has grown that rapidly for 40 years predictably. So what that has shaped the field in some important ways. One of the most important ways it has shaped the field is that when it comes to computing power, people who wanted to deal with information in the abstraction sense didn't have to worry about, my algorithms are slow this year, but next year they will run fast. See, that makes abstraction possible. Right. I don't have to worry about this dirty things you're talking about.
Right.
You will take care of it,
right?
And it will just slow us down,
right?
But next year we'll catch up.
It'll be better, yeah.
Okay. Now, when that doesn't happen, what then?
Yeah, Microsoft would make their operating system more complex every year, and it was okay because the hardware that was running the operating system was getting faster every year, so they had things to do. What if they can't do that?
So they didn't
anymore?
have. They just had to worry about features. They just had to say, "Hey, the user would like this cool thing to happen."
Yeah, dark mode.
And it doesn't matter. It doesn't matter if it basically takes 3 times as much code to do this thing, and it runs 2 times twice as fast because those guys over there will solve the speed problem next year.
So,
But imagine a world where it's not getting faster 2x every year.
right.
Now the computer scientists have to say, no, I have to worry about it. I can't just simply throw in 3 times as much code.
Well, this is new infrastructure. I mean, this
This is the new way of thinking.
right.
And the computer scientists will have to bend.
Computer scientists will have to start thinking more like electrical engineers.
They need
in
more
some
EE
of the
background.
fields. In some of the fields, some of the parts of computer engineering. Things like, things that you're doing mostly on the phone, etc. You may still not have to worry about it because we are at a place, as you said, the added value of a faster chip is sort of negligible, right? For most of the apps you have already.
Right.
VR could push you a little bit more.
Yeah.
Already the retina displays are kind of better than most of us can see.
Exactly. Beyond the eye can cover.
Beyond the limits of our eyes. Okay, so VR maybe basically V and other 3D things basically they could basically push us, but mostly for 98% of what we current usage is, unless there's a killer app that opens up those dimensions.
Right.
These things will be written the same way as written now, information plus abstraction from a software point of view.
Right.
Hardware people will keep packing them to 100 billion transistors and batteries and everything in close proximity with each other and doing this thing, right? But when it comes to basically solving the hard problems of tomorrow, recently we've had this prediction of this Hurricane Dorian and keeps changing, right? And it keeps changing every year, every day. And the reason it changes every day is not because that's how it is. It changes every day because our models are not rich enough.
Right.
And the reason the models are not rich enough is because we don't have enough computing cycles.
So this is what's been eye-opening to me in this conversation, and stay with me for a little bit because I'm going to fumble through this. But I believe that we run into the same problem of explaining electrical engineering to high school students in the same way that we have a lack of interest in another field of engineering like civil engineering. And that's what I'm saying, stay with me for a second.
Yeah.
Because infrastructure is known and complete in our current world around us. And so it's hard to imagine the future new world problems. Right. It's a given. I open my tap, I have water. Right. I flush, it goes away.
Right.
We're not needing
the buildings, the bridges, they're all there, right? We know how to do them. They last for a while.
There isn't a common worry about water and flushing and infrastructure, and there's tweaks and improvements, but someone will do that, and that's not revolutionary. What I'm hearing today is I could see it from a high school student perspective, that like we talked about with the Amazon distribution centers, it's not physical. It's just I have it, so therefore that means it must be a software problem. And so I think that's just the light went off for me, no pun intended, with an electrical company. Yeah. But this went off for me that there is so much happening that we need to build that doesn't exist right now, and these pathways that do not exist. And it's a whole new way of thinking than for the last 40 years or 50 years from Moore's Law.
That's right.
That systems beyond Moore's Law is not about how do we build at a faster rate because we're beyond Moore's Law. It's how do we think in an entirely different way and create new types of infrastructure for electronics and computing and communication and pathways to the point that you get as fascinating as beaming someone up on a spaceship.
Right.
Because that's physical transmission of people through an optical line, right? In a sci-fi world, right? But we're not doing that, but we are talking about these ideas of computing and 5G. But that all seems like, well, 5G is just the plus 1 on 4, right? You're making your bandwidth.
I understand. But here, so let me first address the specific thing about 5G.
This is not my opinion.
I understand. But let me explain. Let me explain the difference, right? So I'll use this as a sort of a simple way to describe things, right? We are, goes back to Hitchhiker's Guide of Galaxy.
42.
I have my towel.
And goes back to Hitchhiker's Guide of Galaxy, which basically describes humans as basically, people who think digital watches are a pretty neat idea. Okay?
Right.
So most of us are fortunate enough to be contented with our lot in life in the sense of creature comforts. We think that the world is basically sort of sorted itself out, right?
Right.
So we think that we basically, because
That's
we
my
have these
point.
devices, we have all the communication that we want.
Yeah.
Because we have these devices, we think we have all the computation we want.
And the majority of us started our lives without any of these things.
And I started with without a computer, right? I
Right.
learned to write programs before I could have access to computers. I would write programs on a piece of paper, and that's all I had to. And the only way I could verify the program was correct is basically to manually check and take some examples and run manually my program, because I didn't have access to a computer. That's how I started learning how to write computers.
Yeah.
When I, first able to basically get to a computer, then it was a different day for me.
Right,
Okay,
right.
so we are. I think it's a good thing for human beings to basically be contented with our lot in life and think that these are solved problems. But in reality, what is happening is that there are several types of problems where essentially we are nowhere close to basically achieving to be able to solve. There are several important problems that we don't know how to solve. I mentioned one of these problems basically, which is this, being able to predict hurricanes, being able to do long-term analysis of any kind of a complex system. This is something that requires huge amount of computational power. And we basically are not there yet. The reason we basically have to update, it should be considered as a failure on our part that we actually have to update our weather forecast every day.
Right.
If you could predict the entire season, right?
Yeah.
Then the farmers could decide whether or not it's worth planting soybeans this season or not, right? Or we could basically figure out how to basically reroute water from somewhere else to here and start basically doing this, right? So the horizons of our imagination, we have to basically expand. Let's get back to 5G to make it more concrete, right? We can always have more of something, but concrete. What this 4G cannot do, 5G is not just a bigger pipe, okay, which will get more data.
Right.
Okay.
It's not about bandwidth.
It's not just about bandwidth. It's also about what is called latency. So right now what happens is that if I send a signal through here, it takes a certain amount of time to go there, and they have to do their thing and send it back to me, give me a response. Okay. And so what happens is that you have heard people being interviewed on satellite network, right? On TV, right? And then if they are in Beirut, you basically, and people know how to, and people who are experts, they know how to fake this thing, right? They will basically ask the question and they will nod and they will nod and they will nod until actually the signal comes, because they know that they are basically,
Right. CNN, yes, the CNN interview. With
you will see that, right? But it's impossible to do robotic surgery through cell phone network today. It is impossible to control if there are sensors over here and if there's a nuclear power plant over there, and it must use information from here, and within a few milliseconds the information must get there and it must take actions, and then this will change, and then if there's basically this give and take,
Right.
it's impossible for you and me to play music together using this network today, unless we train ourselves.
Right.
And music is a little bit easier because you have a script, I have a script.
Right.
So we are somehow, when we are playing together, we are actually faking it.
Right.
Or at least I'm told. Because my musical abilities are below zero, okay? But so I'm told.
Right.
Music is basically, because we basically have our scores, we can actually fake playing it together. But in reality, if you were truly improvising, we couldn't play music over this network today. But with a 4 millisecond latency, a lot of those problems get solved. So instead of 40 millisecond or 20 millisecond or 10 millisecond, a 4 millisecond latency allow you to do those problems. So the thing is that these devices have enabled a lot, and that should make us happy. But if you're truly an engineering student, it should not keep you happy.
That's the issue.
That's the issue.
And
it's not just about more of the same.
That's what I'm
It is about fundamentally new problems that you're solving.
Right.
It's a fundamentally new way to look at life.
Exactly.
And look at our systems and look at our life, liberty, pursuit of happiness. Okay, it's a fundamentally new way to do it. And a 1 millisecond latency network, which is not even 5G, would make even more things possible remotely.
Right.
So you could do telesurgery. You could do telesurgery on a on a goose that was flying in midair, migrating, from northern parts of Canada to basically somewhere in Amazon. Okay,
Right.
you could basically do telesurgery on a goose in flight if it was 1 millisecond latency. Right now, you would have to have me sit down somewhere for somebody to do telesurgery on me.
Yeah.
So it's this thing. There are similarly the reliability of the systems are, some years ago it has improved a little bit. But for example, if you were, I don't know how many of you have landlines, but even many people who have landlines use voice over IP.
Yeah.
Okay, and basically every voice over IP provider will today tell you that this is not, they basically have some Weasley language about 911 calls, because they're not guaranteed to basically provide the level of reliability it requires for you to basically, for it to be your lifeline.
Right.
Okay. So we think that we have voice over IP, so we basically have this great network, right?
Yeah.
But it's not doing some of the things our poor old telephone line system used to do. We have not been able to achieve the level of reliabilities to do those kind of things.
Accuracy.
We have not been able to basically guarantee, even with cell phones, we have not
you
been
are.
able to achieve the level of guarantee of basically your location. And we basically have location information that is basically unreliable by more than this thing. We can get barely sometimes 5 meter, 8 meter, and if you're in downtown among long tall buildings, your GPS will suddenly start freaking out and ask you to take all kinds of turns.
Oh, yeah.
When it doesn't do that, right?
Right.
So you can't use it. You can use it as a human being,
Right.
but you can't use it for autonomous
No. And everything that we're going.
at that level, right? So today, we are happy with the autonomous, especially I have this person sitting next to me, my friend Peter here, who's happy with this thing. In fact, I was scared because one of my colleagues told me that his Tesla can, even though it's only rated to self-drive on the freeways,
Right.
he drives it on the local roads. And then
Yeah.
somebody asked him 2 minutes later, does it have a module to understand traffic lights? He said, no. So I said, dude, what are you doing? You're driving, you're using on local roads. It's
It is
coming.
It is coming.
So, but actually, so speaking of
It's coming, but
Teslas,
but what is not there? Let me finish my point, right? What is not there? If Tesla, when there is accident, a company like Tesla is basically relying on a contract clause that you signed,
Oh, yeah.
okay, to get out its liability. The day Tesla actually doesn't have a contract clause absolving itself of liability, then I would say we have autonomous vehicles.
Got it.
We are not there yet.
Well,
And
so-
that's a
so-
fundamentally different thing.
so
Would you put your child to go on a vehicle alone by herself,
Oh, of course not.
to go on a vehicle, autonomous vehicle and be taken to school? That level of reliability we do not have in our sensors, we do not have in our communication system, and we do not have in our algorithm. So the world looks very different. We can be happy with what we have, and we should be. But we should also be impatient to reach this other land, which is not just more of the same, but it is.
Entirely different.
So this goes to another area. So I have a Tesla. I love my Tesla. It gets a software update every couple of weeks, which is absolutely beautiful.
Yeah.
But it also scares me. I grew up. Well, one of my favorite movies is I, Robot. I don't know if
Yeah.
you remember I, Robot, but this is where
Will Smith.
Will Smith. A malicious download turns all the robots, against the human race. Right.
Right.
What prevents a malicious person to take over, Tesla main campus and just download
A malicious update to
a
you.
malicious update to all the Teslas, such that the next day the Teslas at a certain hour go crazy,
Yeah.
right? How we don't have secure enough systems to prevent those kinds of hacks. In fact, very recently, even every computer chip in every laptop has shown that it has a flaw and that it is more easily hacked, right? So we as electrical engineers need to really be thoughtful and careful about the system design that we're doing, that we need to do, to not only make it more reliable in the sense that just with no one hacking it, but also recognize that there will be people who are trying to hack our systems. And we need to protect against that. That's an even harder problem. But given how fast this technology is just taking over everything, and it will because it's wonderful, we have as electrical engineers to keep up and make it reliable and make it robust to that kind of hacking.
So I don't want to keep you because we've been here for a while,
Yeah.
but here's what I'm hearing, and tell me whether you agree with this. From a high school student's perspective that has a hard time understanding a black box of engineering school and graduate degrees, but they do understand end output. They see autopilot on a Tesla. They see cybersecurity, or they understand cybersecurity and hacking. They understand wireless communication and devices. They understand computers and signal processing, but they don't put
Maybe a
a name on
little
it.
abstract, but they MRIs, they may understand all the images they see in terms of brain scans and whatnot.
Right. They see these things that occur, and they understand the potential for devices that don't exist yet.
Right.
And electrical engineering, a degree in electrical and computer engineering, will have a larger impact in the future of all of those areas than any other discipline.
Yeah, absolutely.
That's how I want to end it.
Yeah, very good.
Thank you very much.
Thank you.
Thank you. That was awesome.
So that was a super in-depth conversation
Yes.
about electrical engineering, computer engineering, and everything in between. And I hope that everybody really, there's a lot to unpack, but hopefully that last point about like nothing is going to impact all of these little things more than electrical engineers. That doesn't mean that computer scientists and mechanical engineers and other types of disciplines are not going to be involved in that process, but it all centers around this. I mean, like that's where I liked your comment about avionics.
Yeah.
I mean, I think that's a really interesting kind of.
I think so. An interesting thing about that in particular, I think if you just to relate it to why electrical engineering is so important, and of course avionics for RPL is more than electrical engineering, but it's an electrical system, right? But as you know, both professors mentioned, you can be working on electrical engineering, not be an electrical engineer.
Exactly.
I think if you think about like the constraint for success for a project, like the minimum constraint, that is kind of where it relates. So for example, avionics is the system on a rocket. And in the case of Rocket Propulsion Laboratory, avionics deploys our recovery systems and also collects the data about our flight. And I would say sort of the minimum constraint there is that we need a parachute to deploy in order to recover a vehicle, and we need to collect data in order to prove how far a vehicle went into space. And without those two things, the flight is
useless.
I mean, I don't want to say
useless
useless in the sense that you can learn a lot from it, but you can't prove you went to space, for example. And we experienced this.
You can't learn as much.
In the past year, where in the fall, due to a procedural error in our launch, our Traveler 3, this rocket, performed nominally the motor burn to completion, etc., all of these really amazing technical feats of engineering, but without the electronics to record that, we didn't go to space, right? Even if we did. So, once you do have that, it's so much more powerful. And I think kind of in a number of other areas that we just discussed today as well, like, yeah, you can, write whatever
program. Is
program.
likely the second time you guys went to space, but you don't know that.
Exactly. And I think that's true with a lot of other problems in mechanical engineering as well. Like, you need some way to record data, and that often involves some sort of electrical system. So I don't know if it's necessarily like the system that's going to, carry all these innovations, but, any sort of engineering involves every kind of engineering, I think.
Absolutely.
And, like even what we were talking about with civil and electrical engineering and how, people don't understand because this infrastructure is already there. With like cloud computing, you need data centers that are using civil engineers to design it because they have special cooling systems. You have mechanical engineers working on sensing systems along with electrical engineers working on servers. And of course, all of that is powering the cloud. So everything's interconnected, and that's what's cool about it to me. But
Exactly. That's a really good, and that's a much better ending point. But I guess the reason I say that is also because of how we structured the conversation, or what was the inspiration for the conversation was nationwide this over subscription or overly enthusiastic interest in something just called computer science, and that is such a small element of all of these things. Because someone is interested in cybersecurity, they think computer science. If someone is interested in computers, they think computer science, and there's all these other elements that go into that, including cooling units and everything else that happens from other disciplines.
Yeah, and I think one thing you know, for me at least, kind of thinking back to high school, I'm very much someone who is always interested in something grounded in some sort of physical constraint. So that's kind of what drew me to mechanical engineering specifically. But I would say that one reason I think culturally we're drawn to computer science right now just because of our interest in tech. But I would also say sometimes too, perhaps electrical engineering is maybe a little less accessible. Like, you know, almost anyone can learn how to code now in a basic way on their computer through so many programs online. I think mechanical engineering, for me at least, seemed...
It's far more involved.
Or it's just something you can picture what it is. Whereas for me, as someone in high school, maybe I would have been interested in electrical engineering, but I just had no idea what it is really, right? Because we don't directly engage with it.
This is similar to, I'm going to fumble through this as well, but this is similar to the ideas of access and equity in sports. You know, why are golfers not as diverse as other sports? Well, the impending cost of going for a round of golf. Like, first of all, is a golf course next door to your house.
Right.
And then you need these clubs, and you need this whatever. And golf is like this one kind of barrier. But like playing basketball, there's a court over there, and there's one ball, and there's 10 of you, and you're able to play basketball. And then there's various sports in between where you have different access and equity to that level of information. And that's similar to computer science now.
Right.
That people have access to coding and software learning online, and they have way more access to that than they do this complex circuitry system or 3D printing or anything else where they can understand mechanical models or something that's just a little out of reach.
Exactly. Like CAD software is so expensive in the case of mechanical engineering or whatever. So I think, you know, that's something anyone who is already, you know, been empowered by engineering or already within that community can like work on them, because there are ways you can make it more accessible. I mean, I know this summer Celeste and I, another BSA, we volunteered at a Microsoft program called DigiGirls, and we did an Arduino activity, and everyone took an Arduino home at the end of the day, which is awesome because then you have this like real physical thing that corresponds to code you're easily writing on your computer.
But I guess that's the thing, is that Arduino's perfect.
Yeah.
And anybody that's interested in electrical engineering typically right now has had some sort of experience with that.
Yeah.
But how much does an Arduino cost?
I think it's like $20 maybe. I honestly don't know.
Even if it's 20, it's more than the free course.
Exactly. And yet you have to, there's like something that's a little more challenging. It doesn't have the same like, I don't know.
Follow these instructions and learn how to code and write this out, but you have to be there with them.
And like get a physical thing. Yeah, and I think there's something to be said too of like perhaps the instant satisfaction of like compiling code and having it run, whereas, you know, building something physical takes so much more time.
The instant gratification.
Yes.
That totally. So.
But there's something also really satisfying about building a piece of hardware and having that work after iterating it, and, you know.
Yeah, I totally thought like 5-6 years ago this was all going to be solved with Raspberry Pis. Like, I thought that people were going to be building contraptions that they coded with all these little apps that were coming up, because after the App Store explosion, there was like the Raspberry Pi app thing, and then it just didn't go anywhere. I think it's just because there was not instant gratification.
Yeah.
People could build little contraptions in their house that were controlled by an app, but then it was just like, it's too hard.
Yeah. But I will say, you know, at USC, there's so many resources, of course, as an engineering student, and so many ways to sort of get a taste of that hardware in a pretty accessible way. So even with RPL, we do all of our PCB layups in-house.
What's PCB?
Printed circuit board.
Oh, cool. Yeah.
So, you know, I've been there for those, and it's just really fun, and you can learn a lot in that amount of time by actually playing with the hardware and building it yourself. So I think my message there is that once you're in school, or at least in my experience, there's so many ways to learn about electrical engineering. We have the Fab Lab for in the case of mechanical engineering, where you have free access to use 3D printers, mills, whatever. So many universities can provide that platform that you might not have at home in high school, at least.
Right. Well, cool. What else is going on with you?
Um,
Sorry, we've talked so much about EE.
yes, well, as people may have heard my coughing in this, I'm getting over my annual beginning of the year cold.
Well, that's good.
Yeah.
Good. Your immune system's catching up.
Yeah. But yeah, just classes. This is our third week of classes now. It's already flying by. It's insane as usual. But yeah, it's just been fun.
Mech Op is heating up.
Yes, MacOps is always a topic of conversation. I have not had my lab this week, so I can't comment
So you're
additionally.
okay right now?
I'm okay right now. But
It's early. It's early in the
yeah,
week.
it's still early in the week. But yeah, I'm trying to think. Last weekend we had a great USC football game. USC football's back. So much
Yeah.
fun.
That game was amazing. You were at the game?
Yeah.
Yeah.
Yeah, and I think I feel like last year the games weren't very fun because
It was a struggle.
yeah,
It was a struggle.
it's a little harder to be super spirited. But this game, like the student section was full the whole time, and it was just fun.
For those just listening, we were recording this after USC beat Stanford decidedly.
Yes.
And it was a killer game. It was a fun game to watch. And Keaton Slovis, true freshman, he looks so young. Looks so young. He comes out and has this record for most total yards and most touchdowns by a true freshman.
Yeah.
That's an amazing stat.
Awesome.
I think I'm probably going to get beat up by people who listen to this. I think the last record holder for that was Matt Barkley. And so that comes in and is that wrong? Do you know?
I don't know. Yeah.
Yeah, but I'm pretty sure that's what happened.
Yeah. Yeah. I went to the USC Stanford game last year at Stanford, and it was
Troubling.
yes, it was very sad. A different tone.
This was exciting though. This was really, really exciting to watch. And,
Yeah,
and
it was awesome.
It was cool. It was very, very cool. And for us in admission, you know, we talked about it last episode, but we're on the road and we'll be out there. There's, you know, obviously you can go to viterbiadmission.usc.edu to see where we are. And I will be on my way to Shanghai rather quickly here. Probably by the time this goes up, I'll be on my way and on that really long flight. And then, so if you're going to be in Shanghai, please come say hi. And also in Taipei. And our colleagues will be in other areas as well this upcoming week in Phoenix and Denver and Hawaii, San Diego. And then all of us will be meeting for our conference in Kentucky the week afterwards. So lots of travel, lots of planes, lots of miles, lots of hotel rooms. But if you ever need anything, just please reach out and we'll get back to you as soon as we can. Other than that, I think this is a good place to say goodbye.
Yeah. Thanks for tuning in.